much, and happy New Year to everybody. I see that I'm missing a lot of fun actually in Chile, in Santiago. I wished I could be with you, but unfortunately this was too difficult for me to participate in person. So yeah, it's my pleasure to present actually our work here at this summer school. It's called actually here in Germany, but yeah, for you it's a summer school. So and as you mentioned, I have been working on humanoid robots since more than 20 years. Actually, when I started my PhD, developing robots which should support humans in daily activities, in particular in household tasks. And in this talk, I will give an overview about the progress we made actually in the past and give a few ideas about future research directions. So before starting, let me thank actually my group, a wonderful group and interdisciplinary team of students and PhD students from computer science, mechatronics, electrical engineering, physics, and mathematics. And this reflects actually the interdisciplinarity, or at least part of the interdisciplinarity of robotics. Of course, cognitive scientists and maybe neuroscientists are missing in the team, but we are engineering oriented school here or university, and this is the same also in my team. We are working on humanoid robots, in particular humanoid assistance robots for daily tasks, as I mentioned, but recently also we managed actually to demonstrate that these robots are able to perform tasks in industrial environments in form of collaborative robots. We work also on wearable robotics, so prostheses and exoskeletons. We developed the entire mechatronics for these systems, taking into account the requirements of robotics, actually, where you have, of course, constraints regarding integration of hardware, of mechanics, electronics, and so on in very small space. To program these robots, actually, we rely on the paradigm of programming by demonstration, imitation learning. So we would like to have robots which are able to learn from humans, to learn from interaction with the world. And therefore, we analyze human motion intelligence and try to understand how humans perform tasks in daily tasks, and try to use this knowledge about human motion intelligence in order to program humanoid robots, which are robot systems with high number of degrees of freedom, in order to perform not only one single task, but versatile tasks as daily tasks. And of course, in order to do all this stuff, you need to integrate things. Integrating things does not only mean putting things together in order to build the system, but putting algorithms, software, and hardware actually together in complete architectures, which integrate perception and action, integrate symbolic information and sub-symbolic information into coherent architectures, which are hopefully also transferable, not only usable on one single robot we developed, but also transferable to different robots. But in particular, our research goals are actually the engineering of these systems, really how to build these systems, which are not task-oriented, which has not been developed to perform one single task with superhuman performance, but to perform a wide variety of tasks. And in many of these tasks, we are targeting like daily activities, like support of technician in industrial environments. Grasping and manipulation is key. And grasping and manipulation, as we know, is the ability to change the state of the world. And intelligence is also the ability to detect change and adapt to change. And therefore, I believe manipulation and intelligence are inseparably intertwined. and a core requirement for robots which should help us, and companions which should help us at home. As mentioned, learning from observation and from experience is the third goal. And the second one is the ability to naturally interact and communicate with humans. This is a research goal which is actually covered by a colleague of mine, Professor Alex Weibel, and not by myself. So we have developed several humanoid robots. So the ARMAR robots, you see some of them here on the slide, the ARMAR 1, the ARMAR 2, the ARMAR 3A and B, and so on. Now we are working with the ARMAR 6, and we are developing the next generation of these robots. Grasping and manipulation requires also hands, which are able to deal with wide variety of objects. And we believe anthropomorphic hands or humanoid hands are the solution here. We started building pneumatically actuated hands in the past with high number of degrees of freedom, 11 and 14 degrees of freedom here. And we moved from these complex systems actually to more to less complex systems, 3D printed and actuated hands, as you see here, which can be used for humanoid robots, but also for prosthetics. Here are some of the tasks we are working on. This is actually our lab. It's a kitchen environment equipped with a dishwasher, with a fridge, and so on, and where the robot is actually operating and learning how to perform these daily tasks, such as loading the dishwasher, such as bringing objects from the fridge, and so on, while interactively communicating with humans using natural language. I'm a little bit proud of this video, actually. This is my favorite video because I did it in February 2008. And since that time, we are able to perform these demonstration or these tasks in the kitchen environment for almost every visitor, actually, who come to our lab. And the robot is still working. It's 17 years old, actually, and it's still operating. So a little bit more actually dive deeper into what's going on here. It's not only about really the execution of sensorimotor programs, but it's about the integration of symbolic and sub-symbolic information of learning mechanisms into complete architectures, as you see here. An architecture where we have natural language understanding, planning and execution monitoring on the highest level. We have, of course, the sensing and control on the lowest level. And we believe that memories are very important to bridge symbolic and sub-symbolic representations. This is why this mid-level of the architecture, a memory level here, which include different types of memories like prior knowledge memories, long and short-term memories, working memories, and in particular, recently we are developing or working on the development of episodic memories. But what you see here in this video is actually a robot performing a task, helping a human to prepare dinner for 2 people, but by not only executing pre-programmed actions, but by reasoning about, for example, missing objects which are needed to execute the plan. So, for example, the robot can use object affordances in order to replace the salad bowl by the mixing bowl, or it can use object affordances extracted from text mining in order to replace a Coke by a multivitamin juice if the Coke is not available, for example, at home. In particular, actually, we are heavily working on the implementation or the realization of such transferable compositional architectures. And in the last years, we focused on the mid layer, which is the memory layer, actually. and in particular there on the implementation of episodic memories as part of the long-term memory of a robot. And the question is, of course, how to encode experience of a robot. Experience of the robot is everything what the robot perceives with its cameras, with its microphones, the motion, with the proprioceptive sensors, and so on. And the second question is how to recall the experience actually in order to predict actions based on recalled experiences. And the third question is how to use the knowledge in the episodic memory and to make it understandable actually for humans. In other words, how to externalize the experience of the robot in natural language, or how to verbalize that. And this is what we did in the past. You see here first example where, thanks to deep learning architectures, we could actually implement an episodic memory in which we store visual information of the robot about the task, of course, in latent spaces, and use this visual information in order to predict actions and use the predicted actions and also their durations for time-aware planning. You see here an example where a human is preparing breakfast with eggs here. You see the observation and the recalled experience here. And in the video, you may have seen actually that when a certain episode is recalled, the actions associated with this episode are recalled or predicted and used in order to generate a plan which fulfill the time deadlines we have in order, for example, to prepare a breakfast by accelerating or decelerating some of the actions required in the plan. Recently, we extended this work. I'm not going to talk about the detail of the deep neural architecture here. If you are interested, you can read it here in this paper from 2018. But recently, we extended this work in several ways. So the first thing, we don't store only visual information in the episodic memory, but we store the pose and configuration of the robot, object IDs and locations, and symbolic tasks and the actions which are executed together with the time steps for the different action. And we developed two actually deep neural architecture for creating the episodic memory, not only from visual information, but for multimodal robot experience and for the verbalization of the experience in natural language by combining two encoder-decoder models, one which learned the latent representation for episodic memory using LSTMs, and another one for natural language processing using pre-trained transformer architectures. And the goal of that actually, again, the details are described in this paper, but the goal of that is actually to have robots which are able to answer questions. Did you see the red cup? And not questions as we know from Alexa and so on, but questions related to the tasks what the robot performed. Did you see the red cup? I last saw it at the table 10 minutes ago. And I will show actually a demonstration of this.
I will be away for a few moments. Can you please tidy up while I'm away?
I hope you can hear the sound. So Leonard actually said, I will be away for a few minutes. Can you please tidy up while I am away? And you see the robot is actually now executing the task, grasping the objects, storing the camera images, but also the configuration, the object IDs, the poses, which are determined, of course, using the visual algorithms we are applying. And building actually or creating this episodic memory, what I talked about with every new data actually. And At some point, you see here the creation of the episodic memory, which include now not only the visual, but also
Tell me what you did, please.
Not only the visual information, but also the multimodal information, including symbolic task information. Now Leonard is back, and he's asking the robot, "Tell me what did you do?"
I moved the multivitamin juice to the countertop.
How long did it take to grasp the green cup today in the afternoon?
It took about 1 minute.
Tell me which object you moved to the countertop yesterday at 2 p.m.
I moved the red cup.
When did you last see the red cup?
I saw it on December 9th at 14:56.
Thank you.
So I hope you could hear actually the sound and the natural language interaction between Leonard and the robot, where Leonard was asking the robot, when did you see the last cup, the red cup? How long did it take to grasp the red cup? When did you see the red cup last time, and so on. And I believe actually these natural instructability of robots, or being able to interact and communicate in a natural way with robots, is crucial and important for the acceptability, but also acceptability of robots by humans, but also for the explainability of robot behaviors to humans. And therefore, we are working on this instructability aspect by asking the question, how can we manipulate the scene using verbal instructions? So ARMAR, put the mustard on top of the rusk, please. This is a natural language instruction which should be understood. We should understand what's the target object. The mustard is the target object, the rusk is the reference, and the relation which must be fulfilled is on top of. Of course, this understanding should also happen in the visual domain. So we have to understand in the visual scene what are the current relations between the objects, so that the mustard is now not on the rusk, and therefore we have to generate an action or a sequence of actions in order to fulfill this relation. And this is very important because humans, as we know, often describe manipulation tasks on semantic level, not on sub-symbolic or level. Yeah. Therefore, the understanding of spatial relations is important and allow the robot to execute such natural language instructions. In order to deal with that or to solve the problem, we learn generative models of 3D spatial relations as parametric probability distributions based on cylindric coordinates. So we describe actually spatial relations not in Cartesian coordinates, but in cylindric coordinates, because they are more intuitive to express something like to the left, to the right, far or close than Cartesian coordinates. We combine Gaussian and Van Mies distributions so that we get very few interpretable parameters to describe these relations, where these distributions are learned from examples demonstrated by a human, and where we can sample from these distributions to generate candidate target positions which fulfill the required relation. So you see here, actually, these parts here in the scene are all positions in the space, in the Cartesian space, which would fulfill the relation mustard on top of rusk, yeah, or object on top of rusk. And once we learn that and we sample from this distribution, then it's of course very easy for the robot to execute the task, because as we know, the robot needs a Cartesian position as target position for the action in order to place the object. And this is what you see here in the video. And we do that not only for one relation, but for other relations. As you see here, we have other spatial relations, like something is on the left of something. So move the apple T roughly to the left of the kernel bar, or put the apple T on the other side of the kernel bar. So these are examples from our work on companion robots for daily activities. But as I mentioned before, 5 years ago, we were part of a European project, the Second Hands project, where our task was to develop this robot, the ARMAR 6 robot, actually, which should support technicians in industrial environments. In particular, in maintenance tasks in these fulfillment center of Okedo technology, where you have actually these conveyor belts, which you see here, which should be maintained and repaired 24/7, actually. And this is how the tasks are done currently. You have two technicians. One of them is the expert who knows actually how to do these maintenance and repair tasks. And the other one is a technician supporting the expert actually by carrying heavy objects, by handing over the next tool, and so on. And our goal of the project was not only to develop the robot in terms of its mechatronics and software architecture, but to endow the robot with the ability to recognize the need of help. So the robot should recognize the need of help and provide this help in a proactive way to a human. And this is a demonstration, actually, if you what we showed at the CeBIT 2018, where the robot was able to recognize the need of help based on visual information and interpretation of the current scene. You see here there is only one technician. The task requires two, and therefore the robot starts helping Pascal here in lowering the guard and placing it in a different position so that we can repair the task. So actually, a few weeks ago, Yuki visited us here in Karlsruhe, and she saw the demonstration, and she can tell you her impression. She was also moving the guard together with the robot here in our lab. So recognizing the need of help is really very difficult. And as I mentioned before, this can be done based on visual scene interpretation and our knowledge of the task. This can be done also based on force information. When you carry a heavy, large object together with another human, the force profiles, actually what you experience, can tell you something that your cooperating partner is in need of help. But the easiest way is, of course, speech, to recognize the need of help based on speech, either by direct comments, please help me to do something, or by indirect comments like, oh, this object is heavy. And then the robot should, based on that, infer actually that its help might be required. You see here some of the tasks actually where this recognition of help based on force information, based on visual information, interpretation also of the intention of the human, like the handover here, is executed and is performed. And we were very happy actually that we could also conduct experiments in the warehouse environments for 6 weeks, where technicians were able to work with the robot and execute these tasks in the real mock-up environment. So the second application area we are working on with the same robot, actually, with humanoid robots, is decontamination of nuclear installations. So Germany decided to stop nuclear energy a few years ago, and they have to actually decontaminate all nuclear plants. And you see here an example with parts, contaminated parts, which should be cleaned. And this is a human actually who has to pick up these objects from the box, put them on the rotating table, clean them, and then put them in a clean box. And we would like actually to remove the human from this decontamination cell by using our robots. And the question is for us is actually how to grasp and manipulate these arbitrarily shaped objects in these boxes, and with not so many features. Actually, they are hard to detect and to localize based on visual information only, and we don't have any model knowledge about the objects. And therefore, we actually apply affordance-based grasping methods, which we developed also in the past, where agents actually or where we generate grasps or actions for our robots based on the interpretation of the interaction possibilities with unknown scenes. So you see here a cluttered scene. This is a box actually with these contaminated objects, and based on this visual representation of the scene, the robot has to actually identify or extract the affordances. Which part in the scene affords grasping, pushing, lifting, or which or support? Yeah. And with that, we were able actually to develop an efficient but yet not perfect system for grasping and manipulation these difficult and unknown objects. And you see here examples where the selection of a grasp is done either manually by the human by clicking on one of the extracted affordances, or by a human in using VR, AR glasses here and selecting the best grasp here, or autonomously actually. And the first results here showed that the semi-autonomous grasp selection reduces the error rate to 28% compared to 43% in the case of the autonomous execution or the autonomous grasp selection. This is very promising for us, and we are continuing actually the work in this area, because the question is for us it's actually a question of grasping difficult, unknown, and heavy objects. Yeah. And you see here in these examples, only single-handed actions are used in order to lift these parts. We are now working also on bimanual manipulation in order to generate actually bimanual grasps in order to lift these heavy, usually heavy objects. In the videos you see here, these are also objects in our lab and not the real objects we have to deal with in the real application. So the second part of our work is related to learning from human observation. As I mentioned before, these robots should learn from human observation. You see here examples where the robot is observing a human wiping the table. And the goal is, of course, to learn these actions with all the parameters, the task-specific parameters, so that we can execute the task under different conditions or in different environments. So in this example here, it's not actually sufficient to learn the trajectory form, but we have, of course, to learn the constraints, which is contact with the environment, for example, with the surface, so that we can adapt the learned primitive to different conditions like wiping actually concave or convex surfaces. And the idea is, as many people actually in the field, is to learn this famous library of motion primitives and use these motion primitives or sequences of these motion primitives in order to perform complex tasks. And crucial is actually the way how we represent these movement primitives, and therefore we developed here a new formulation which we call via point movement primitives, which allow us to learn these motion primitives from multiple demonstrations and while taking into account the different modes and the different modalities in the demonstration of the task. And the idea behind that is that the trajectory or the motion primitive is composed of two parts: an elementary trajectory, which is a spatial trajectory that connect two via points. They could be also the start and the end point, and could be a linear trajectory or polynomial trajectory, where you can specify acceleration, jerk, and so on along this trajectory. And the second term, F, which is the shape modulation. This means a probability, of course, to allow also learning these primitives from multiple demonstrations, a probability distribution which model the offset from the demonstration Y to the linear trajectory or elementary trajectory edge. And with the help of that, we can do things like that. Once you learn such a movement primitive for reaching, for example, and you would like to adapt it in order to execute the task here with the ruler in the hand, which doesn't pass actually here due to collision because it would collide with the ladder here. So you include a via point in the middle without a complete relearning of the movement primitive we learned before. Again, here for the collision avoidance, you can include a via point around the obstacle here so that you can grasp the object without a complete relearning of the previous of the movement primitive. With these via point movement primitives, we are also able to actually adapt them and generalize them to different task constraints. You see here, we use mixture density networks in order to do this generalization, but the robot is able actually with the learned movement primitives here to generalize. You see here, the goal is to hit this target here with the ball by either throwing the ball directly to the target or throwing the ball to the wall to bounce back and to hit the target. These are isolated actions like wiping, like throwing, like grasping or reaching, and so on. But we are really interested in these whole body actions, yeah. And we are interested in building this, what I used to call robot internet of skills. And therefore, we collected a large amount of whole body human motion data. In total, we have 42 hours of manually labeled human motion data, including object information, not only the motion of the human, but also the object information, as you have seen here, the object information. We use also a reference model of the human body here in order to unify the data, to have a unified representation independent of the teacher, whether the teacher is large, small, tall, short, and so on. And you see here the object information, and we can actually retarget the motion here, the human motion data here, to this reference model of the human body, so that we have unified representation on which we can develop our algorithms and from which we can map also to different robots. Of course, in order to do that, you need to understand or interpret the demonstrations. In other words, you have to segment actually the human demonstrations in the most important parts. And this is what we do here, where we segment whole body actions in trajectory segments, which can be, for example, represented by via point movement primitives. And we can do, of course, biomechanical analysis of all these recordings. You see here the center of mass trajectory, the angular momentum trajectory for this motion. And the goal is, as I mentioned, to actually generate motions for humanoid robots. The database is publicly available, is maybe the largest publicly available human motion database. And the software which you need, for example, for retargeting, for visualization, and for segmentation is also available, publicly available for everybody. So, but the question is actually how to use this data in order to generate whole body motion and whole body motions. So you are working then in a high dimensional space, and we were thinking about how we can deal with the complexity of this high dimensional space. I mean, the model of the human body we're using has 104 degrees of freedom. And therefore, we're thinking about principles which can simplify the generation of whole body actions. We came up with a taxonomy of whole body poses, which consists of 46 classes, as you see here, and where these classes are defined by the number of contact with the environment. So the first row you see here, we have only one contact with the environment, like single foot support or knee support. here we have two contact with the environment, like double foot support or foot support and hand support, and three contact with the environment or four contact with the environment. Of course, we distinguish different contact types, like lying contact, like playing contact, like holding contact here. And we developed this taxonomy where also the lines describe transitions between the poses. So if you are in the kneeling pose and you would like to go to the single support pose, you see that you have the transition from 1-2 to 2-7 and from 2-7 to 1-1. If you have a door handle next to you, you can go down from 2-7 to 3-12 and stand up, go to 2-2 while holding the door handle, and then go to the single support pose. So in other words, actually, we have a kind of grammar through this taxonomy, which describe for us the sequence or the transitions between different poses in order to generate a whole body action. The taxonomy is very much inspired by our work on grasping, or by taxonomies proposed in the grasping community. You see here, we are actually less stable in this area of the taxonomy, but more mobile. And here, if you are lying on the floor, you are of course very, very stable, but less mobile. And this is maybe how this taxonomy was actually developed, where we looked also to Katkowski, Kamakura taxonomies in grasping and tried to figure out how we can provide the taxonomy for whole body actions, because there is actually a duality between local manipulation and grasping, and this is what we use here as basis for this conceptual design of the taxonomy. But we validated the taxonomy with human motion data. You see here the example I showed before, and this whole body action actually can be described by this sequence of poses of the taxonomy, with these transitions as you see here in the automatically generated graph of transitions, where you start with double foot support, you lift one leg, and then you have again double foot support. While double foot support, you touch the handrail. While touching the handrail, you lift one leg, and so on. And based on that, you see you can actually describe these whole body actions by sequence of poses of the taxonomy. And we did that for many activities, actually, as you see here in the example. And we were able to generate these actions, these whole body actions, as sequences or poses of the taxonomy. And we were also able to generate multi-contact whole body motions in times which are much shorter than times what current state-of-the-art algorithms need, because we use natural language models, N-gram models, which predict the next pose in a sequence given the last n-1 words. But back to manipulation, from whole body action to manipulation, and recently we are very much interested in bimanual actions, understanding bimanuality in humans, but also bimanual actions for our robots, in particular, for example, to lift heavy objects, as I mentioned before. And similarly, we started, of course, collecting or have a large amount of data, and we started looking at categorization, actually, of different types of bimanuality in human actions. And we came up, with another taxonomy, which is a bimanual manipulation taxonomy, where we classify bimanual manipulation tasks on the highest level, coordinated and uncoordinated tasks. So the goal is, of course, of this taxonomy is to support learning of task models for bimanual manipulation from human demonstration. And of course, the execution of these task models on robots. And you see here the first level is concerned of the taxonomy with the question of whether there is any kind of spatial or temporal coordination between the hand. So uncoordinated movements are in principle simultaneously executed unimanual actions. This means an action is uncoordinated if the same result can be achieved by executing the action consequently in arbitrary order on a single arm. So unimanual activities are subcategories of this category, since one hand just fulfills no specific purpose. For example, uncoordinated bimanual action is one hand holding a coffee cup while the other hand is taking notes. Yeah, you see here in this example. So within the category of coordinated actions here, we go deeper and we look into the interaction and the symmetry of the execution of the actions and the role of the hands. For example, what's the dominant hand in the execution of asymmetric, tightly coupled action? So this work has been recently presented at IROS and in RAL. If you're interested, you are welcome to look into that. But again, to validate this taxonomy and to understand how we can extract these bimanual categories. So it seems that we have bimanual categories like asymmetric, tightly coordinated, tightly coupled asymmetric actions where the right hand is dominant or the left hand is dominant. And we would like actually to extract these categories from human demonstrations. We did that at the beginning with marker-based data, where we collected this data. We construct contact graphs where the nodes are hands and all objects, and the edges are contact relations between the models, 3D models actually of the hand and the object. We use motion feature extraction methods here, based on velocity and so on of each node. So we assign the nodes to different groups of the left hand, groups of the right hand, groups of the surface of the background or of other objects in the environment. And we developed a rule-based classification system which can tell us actually what's the current category of the bimanual activity. And you see here some examples. Still everything using mockup data, but you see here we had tightly coupled, loosely coupled. Now we have tightly coupled with the right hand as dominant hand, and so on. Of course, the classification, which I mentioned before, and we are still working on some of the, you see here the manual classification, manual labeled classification and the automatic classification. And some of the errors here we detected actually, and we are still working on improving the segmentation or improving actually the classification. So I'm actually very excited that much of this work we are doing on humanoid robots has been transferred or is being transferred to a very exciting research area, which is prosthetics and exoskeletons. So we developed prosthetic hands with the ability, with semi-autonomous grasping abilities. As you see here, the hands are equipped with cameras so that they can actually generate, or they can decide which grasp type is needed in order to grasp which object, and where the user, the human, which is here an abled person, has only to generate a very limited set of EMG signals to trigger the different actions of the hand. So this will reduce actually the cognitive burden on the user. You see here, based on the object, the hand select automatically the grasp based on visual information. All the visual processing is happening on board here using an FPGA on which we implement a deep neural network for the detection of 13 different grasp categories. On the other hand, we are working on exoskeletons here, which are personalizable for the augmentation of human, and which are controllable using non-invasive non-invasive interfaces. So where we rely on force information between the human body and the exoskeleton in order to estimate the intention of the user and the current state of the user and state of the exoskeleton. And we are happy that we got recently actually significant funding in order to continue this work to develop humanoid robots as assistive systems for elderly people and exoskeletons. The work is this is a project with 20 PIs from KIT, where we consider important aspects in the design of these systems, which has not been considered so much in the literature, at least from my point of view. We are actually targeting versatile systems. We're not interested in task-oriented systems, and maybe this is our motivation in building humanoids, understand how to develop systems which are able to perform wide variety of tasks, how to personalize assistance and interaction strategies to different human needs and human behaviors and preferences, and of course the validation of the systems in the real world, which is a retirement home here close to our lab, actually 1 kilometer far away from our lab. You see here some of the results. We are developing the next generation of our humanoid robots. So household robots will be tested in our kitchen environment, which will be extended to an apartment, but also exoskeletons here for the lower extremity. In particular, in this U-Bot project, actually, in addition to the development of these robots, we are asking or we are investigating questions related to privacy and security for assistive robotics. Because for us in robotics, the question we asked so far was always, is it feasible to perform a task by a certain robot? But when you include humans, when these robots should act as assistants and companions for humans, we have to also, and in particular, answer the question whether it is allowed to perform a certain task. And therefore, we are working with colleagues from computer science department, doing work on activity-centric access and usage control in network systems, and trying actually to combine these architectures from network systems and cognitive architectures from robotics in order to answer both questions: the feasibility of the task and whether the robot is allowed to perform a task or not. So the title of my talk was Engineering Humanoids with Motion Intelligence. And this is actually to emphasize a very simple difference between current AI with, of course, breakthroughs in computer vision, in natural language understanding, and so on, where we have huge amount of data and we have new systems actually, and thanks to the data and computing power, which generate information, useful semantic information from the data. This is what AI is about. Robotics AI is actually, we also have a huge amount of data. If we store all the visual data of our robot, the ARMAR 6 robot, we would have 108 gigabyte data per hour. And of course, from this data, from the visual data, from the natural language or speech data, perception, force data, we have to generate semantic information. And based on this semantic information, we have actually to generate motion. We have to generate action, because robots without actions or without motion are useless. And this is what I actually mean with motion intelligence. We have to interpret data, we have to make sense of the data, but in order to generate action and in order to be able also to consider the data generated based on the execution of the action, based on the interaction with the physical world, in order to improve the performance in a continual manner. This is the robotics AI actually I'm working on, and I think many of us here in the room or in the community are targeting and working on to have robots with motion intelligence so that they can act and interact in the real world. They can adapt to change and increase their level of autonomy. Where we have this famous coupling or important coupling between perception and action to generate intelligent behavior. Robots which understands syntax and semantics of actions and continuously learn from interaction with the real world. Of course, robotics or humanoid robotics, and this is one of my motivations actually in working with humanoid robotics, we would like to develop technologies to support humans, but I believe that robotics is also a key thing in order to understand, in particular humanoid robotics, to understand humans and to understand artificial intelligence. The challenges I see is the real world, actually. Engineering systems for the real world, and systems which are versatile, which go beyond task orientation. If these systems should act as companions and assistants for humans, they should be privacy aware, safe, and trustworthy. They should be able to learn in 24/7 manner, to adapt to change. This is the core of intelligence, being able to adapt to change. And robots which are able to interact and communicate in an explainable way and to act ethically. Very important is the acceptance and the assessment of the technology, the consideration of ethical, legal, and social implications of the technology we are developing. And this cannot happen actually by just having us as engineers, computer scientists doing this work. This can only happen by a joint or bidirectional dialogue between society and scientists. And we are happy that we received recently a project from our local state, the Ministry of Research in the state of Baden-Württemberg, where we would like to make artificial intelligence tangible, in robotic words, graspable through humanoid robots. So, and the idea of this real-world lab, that research should be done together with society. We have diverse user groups, as you see here, starting in kindergarten, in schools, for example, where children in kindergarten should learn foreign language and spatial relations by the combination of motion and language of the robot, but also other tasks. We are designing together with the caregivers in the kindergarten, where children in schools are learning actually programming, learning about robotics and AI with robots, but also in hospitals and in museums, where these robots will help people or will help actually the caregiver personnel in their daily activities. So we have diverse scenarios, distributed experiments in the city of Karlsruhe, using different embodiments of the robots, our own robots, but also the Now and Pepper robot, as you see here, in order to make AI, in particular this robotics AI, actually explainable for the society. And I think there is nothing better than using robots in order to explain intelligence and AI for people. With that, I would like to thank our funding agencies, who of course support our research here. And thank you for your attention and also for the invitation to be part of this summer school. Thank you very much.
Thank you very much for the presentation and showing us this amazing body of work. And I would like to give the word to the public for some questions.
Thank you, Tamim, for great presentation. This is Yuki speaking.
Hi, Yuki. Hi.
After experiencing the robot, their object manipulation demo, I'm happy to learn the more details about their behind mechanism. So thank you so much for your great work. And I have the questions about their diversity or the individual differences in the task demonstrations. I think that there, in order to make the robust system, you have to collect many data from many participants, and then to find what's the, how can I say, the core, the demonstrations, the mechanism, and so on. But then there, I guess that the different persons would have different strategies or different order of achieving the task. So in that case, if you apply the simple machine learnings to extract the principle of the task demonstrations, it would just kind of making the averaging of their task demonstration, but it might not lead to the optimal solutions. So in that case, what's your strategies to deal with the individual differences in the task demonstrations?
Yeah, thank you. Thank you very much for the nice and very, very important question. Actually, yes, indeed. I mean, in learning from human observation, we need several examples, and this is what we did. What the examples what I showed for this generalization with mixed density networks, where we can actually take into account the different modes of the demonstration. But so how the human demonstrated the task, whether reaching from the left or from the right. You may have 10 demonstrations from the left and 1 from the right. And of course, when, as you mentioned, when you do this averaging, the one demonstration will disappear completely. And there are some methods, and we did this work with mixed density networks so that we can actually we can account for this one single mode demonstration in the learning process so that the model wouldn't collapse. But your question goes a little bit farther, goes actually towards personalization of the learning of the movement primitives. And I think for that, we need the data. We need again data for multiple demonstrations by multiple humans. And this additional parameter, the different users actually should somehow be considered in the learning process. So that once you recognize Yuki, the robot recognizes Yuki, the robot would apply actually or execute the tasks in the way it landed when interacting with Yuki. We're thinking a little bit in the direction of extending these memories. So we were in this project actually we are aiming at learning user models and linking these learned skills or motor primitives to the user models, so that we have the personalization of the actions to different users with different habits and with different maybe abilities. But so far we don't have any results on that. Actually, we're just starting actually the work in this direction.
Thank you very much. I'm looking forward to seeing the next result.
Thank you. Thank you.
Hi, Tamim. Thank you very much for your talk.
Hi.
I don't know if you can see me, but I'm one of your former PhD students.
Hi.
How are you? So yeah, I was wondering about your take on reinforcement learning for learning for instance, some of the taxonomy you presented on stability and contacts. So in particular, some of the robot platforms you might be interested in using might not have the same kinematics as the human body, so that you would not have the same taxonomy in terms of contact to achieve certain tasks, such as locomotion. And I was wondering, or I was thinking that you would probably want to rely on something like reinforcement learning to find a taxonomy for your robots that have different kinematics than
yeah. Thank you for the question. We didn't think actually in this direction using reinforcement learning for the taxonomy, but using reinforcement learning in order to improve the behavior we learned through imitation learning. So actually, my or our goal would be to use imitation learning to bootstrap reinforcement learning, not to start from the scratch doing reinforcement learning in order to learn a task, but to use the prior knowledge which we already have from human demonstration. We learned in an imitation learning manner in order to bootstrap reinforcement learning like framework. But for the taxonomy, I don't see directly the link. The taxonomy is something conceptual. Of course, if we can use the knowledge of the taxonomy to guide the reinforcement learning search, let me say that, this would be fantastic, but I really don't know how to do it. If you have any ideas, you can come back and continue working on this.
I see. Thanks a lot, Tamim.
Okay.
We have time for one last question.
Hi, thank you for your presentation. My name is Martin. You don't know me, so directly to the question. I was really interested when you told us about that you use FPGA to the robot to arm to do 32 different types of grasp.
No, we actually in this prosthetic hands, which I mean, were developed based on our humanoid hands, and now they will be used as robot hands, the prosthetic hands. So we have a camera in the palm, and this is a 1.3 megapixel camera to detect objects in the scene. And once the object is detected, the hand automatically generates the grasp and execute it when the hand is close enough to the object. And for this object detection, we use an FPGA, which is integrated in the hand. And on this FPGA, deep neural network, CNN, is running, and where we can detect 13 different object classes, like pen, cups, bottles, and so on. And this CNN is implemented actually in this FPGA, where we did a lot of work actually to optimize the architecture of the CNN using genetic algorithms so that you can really implement it on a small FPGA in the hand. If you are interested in the details, we have several publications on that. I can send that to you.
I have, yes, I would like to. I have just one question. If you could tell us a little bit about how did you do the training of this FPGA? Because I'm working in putting architecture of CNN in FPGA. So, did you do the training in the?
No, not in the FPGA. Not in the FPGA. I mean, we did, not on the FPGA. But as I mentioned, I mean, if you are interested, there's one of my PhD students who is exactly working on this resource-aware hardware for fast grasping and reliable grasping and vision-based. So I would be more than happy to talk to you separately and discuss potential synergies.
Okay, thank you very much.
Welcome.
Let's thanks once more to Professor Tamim Asfour, and please, applause. Thank you very much, and enjoy the summer school. And I hope we will have a chance to meet somewhere, maybe at next ICRA in London.